So here's assignment 2. We're going to start with a container that's 0.1 uh, millimeters cubed in volume, and you have water and air in here. The water weighs 1 kilogram. Here's our water, and here's our air. Water weighs 1 kilogram, and then we're given an initial temperature and an initial pressure of initial temperature 298 Kelvin, and an initial pressure of 101.325 kilopascals. And then we're also given in the start of it, we are given another pressure. So our pressure final is going to be equal to 200 kilopascals, but we don't have a final temperature. This is what we're going to be finding right here. Right here, we want to find our final temperature, considering this volume, this weight of the water, and our initial values, our initial temperature and pressure values, and then our final pressure value as well. So what we're going to be looking at here is how to find this final temperature. And the first thing we're going to want to do is add our water and our air pressures together. So the pressure final is going to be equal to the pressure of our water, pressure of H2O, plus the pressure of our air. And this is mainly what we're going to use to help us find that final temperature. And we're also going to use the equation PV equals nRT. This is to do with pressure, volume, temperature, and everything in between. So these two equations are going to help us immensely in the future. So we're also going to be using with our PV equals nRT, we're also going to be using the constant 8.314 joules per mole Kelvin. This constant is going to help us figure out what our ultimate equation is going to help us give. We're going to state this right at the beginning, and we're also going to find out with cancellation that Newton meters equals joules. This is also going to help us find our pressures and volumes. Now what we need to do to find the number of moles of air is take PV and PV equals nRT and switch it up a little bit. So we're going to say the pressure initial is going to be equal to the pressure of the water, H2O, plus the number of moles of air times RT divided by the volume of the vapor phase. So this is going to help us get our moles of air. And this equation is going to be beneficial because we have the initial pressure and we have the pressure of the water, and we can find our moles of air for this. So yeah, that's going to help us. So what we're going to do now is find the volume of our vapor phase. So we're going to say the volume of our vapor phase is going to be equal to the volume of the total minus the volume of our water, because the water times the vapor equals the total. And after that, that can help us find density. To find the density of our water, that's what we need to find next. And density is mass over volume. So it's going to be the mass of our water over the volume of our water. over the volume of our water. And this is the same thing as saying that our volume of water is going to be equal to the mass of our water over the density of our water. So now we can find both the volume of our water and the volume of our vapor. Now we're going to find our how to find our moles of air. We already know the equation for our moles of air. We just need to rewrite it in a way that we can use in the code to find exactly what our moles of air is going to be. So to find our moles of air, we need to use our initial pressure minus our pressure of water, which is going to be a 298, and then times the volume of our vapor, which we just found, and then divide by the R constant times our initial temperature. And that's going to get us our moles of air. Now what we're looking for is our final pressure, or our final temperature. And the way we need to find that is to use an equation and then use a root solver in our Python. So we can find the equation, the pressure of our final is going to be equal to the pressure of water plus moles of air times our temperature final over our V vapor. And then I think times R as well. So what we're going to do to start is we are going to get our data. We're going to start to get our data from the GitHub site. So we're going to come up here and we're going to say, we're going to find our GitHub site right here, Control C, Control V it in here. But we just want it to be, we just want the tools and the data. So we're going to say .git, and that's going to help us. But we need to grab it. So we need to say git clone depth of step one, to get our, so we're going to say run, to get our data. Now, to continue to obtain our data, we are going to import our SYS. So we're going to say import SYS, and then we can say sys.path insert, and this is going to be our one value, and then we're going to grab it from content, and then our CHE tools. And after that, we also need to import our tools, so what we're going to be using. So import tools.che as our CHE. CHE. Okay. We add more code, and we're going to put in our equation. So P equals CHE of our props, but that's going to be our water. So I'm going to say, okay, water. We need to add our these. Okay, and that should just, yes, okay. Good. Okay, so what we want to do here is we want to optimize our equation. So we're going to say from our SciPy optimize, we're going to import our roots that we're going to find. And we are also going to state our R value, which is the 8.314 from earlier. 8.314, and it's going to be in joules over moles Kelvin. Now we're going to add some code, and this is going to be all of our values that we've been given. So it's going to be our V, the total volume, which is 0.1, and then the weight of the water, which is 1 kilogram, and the initial pressure, PI, is 101.13, but that's kilopascals, so we're just going to use pascals, 325 pascals, and we're also going to use our pressure final, which is going to be 2e to the 5, which is 205 kilopascals, and then our TI, our temperature initial, these are all been given to us, 298 Kelvin, which is our initial temperature. Now we are going to input our density. So this is going to be P R dot RHOL of our initial temperature. Got to make sure it's case sensitive. And we also want to use our NAIR code and to input our equation. So it's going to be our initial pressure minus the vapor, the pressure at the vapor rate at our initial temperature, and then that is going to be multiplied by the volume, the total volume. Sorry. Minus the initial weight divided by our PRHOL, which we just defined up at the top, times the initial temperature divided by our R times TI for our equation. Yes, so that should be working, and then we're going to go to our code and we're going to input NAIR and see what we get. So we're going to go up here, say run off. And we have some errors here. So after we have this our equation in here for PV equals PV times nRT, we're going to go into our def PEQ of X. And this is going to give us a chance to import our values once again into a graphical sense. So we're going to say our temperature final is going to be equal to our X, but we need to say of 0. And then our volume of our vapor phase is going to equal the vapor total, or the volume total, which we know is 0.1, minus the weight of I, or the weight initial, I mean, and then times our P, R, O, H, or RHOL value of our temperature final. So after we have this, we have our pressure of the water. This is going to give us our pressure at the vapor phase at our temperature final, and we're going to have our pair equal to our NAIR, I think temperature final. This is going to get us our the partial pressure of water, or the partial pressure of air, and we're going to return pressure of the water plus pressure of the air minus the pressure final, because the pressure final is equal to the water pressure plus the air pressure. Next, we need to say that our root, because that's what we're looking for originally, our root of the PEQ that we just defined is going to be our X, and then our our y is going to be our ti. So now you're going to look at some of the things that might have gone wrong in our code. Maybe we need ampersand greater than dev null. This is just going to nullify everything that that we need in here. And then we have this. Now we need to look at this. So there's going to be a syntax error. It says from SciPy optimize, no module named SciPy.optimize. And look, looks like we've misspelled optimize. Very simple mistake we can fix. Optimize. And that should be a lot better. Okay, all good. And this is still working okay. This one's okay. This is giving us our TI, giving us our values in an array. Here's our calculation of our moles of air that we found on the board. And here are our moles of air. And air is not defined. So our moles of air have not been defined anywhere. It should be up here. It should be defined right here. Let's try to run all. Okay, there we go. And so now our moles of air are working. So here's our moles of air. And now we have the def of PEQ. So let's see. It says invalid syntax, and it's pointing towards the parentheses right here. So let's go take away these parentheses. Let's try it again. Still invalid syntax. Somewhere right here. I think I might need a colon or a semicolon, I believe. A semicolon. Okay. Just a colon. Okay. Unexpected indented block. So this should not be indented. I don't believe it is. Unexpected. Expected an indented block. So it should be indented. All these should be. Let's try this. Okay, it's good. And so let's find our roots. Looks like device array object is not callable. Okay, so it's telling us we have a device array object that is not callable. I think what I first want to do is change this equation to fit more of what we wrote on the whiteboard. So the moles of air times our R times our temperature final, and then we are going to divide that by the volume of our vapor pressure. And hopefully that can help. And there we go. We can find our solution. We found our X, and we found our R here. And the status is 1, success is true, which means this code should be okay for now, and we can move on to the next portion. The next part of this is we are going to figure out what we're going to do if we have 0.3 moles of water. So we are going to say how many moles of water do we want? So water vapor, I mean, sorry. So we're going to say moles of, moles of water vapor desired is going to be equal to 0.3 moles. And we need to make another def statement. Oh, whoops, didn't mean to do that. We need to make another def statement, and we need to say def PQ now 2 of x colon, gotta remember that colon, is going to be equal to our temperature final, same thing we did last time. So 0. And then our volume total is going to be equal to our 1. Just grabbing those values. And then the volume of our vapor, water vapor, is going to be volume total, just our same equation, minus our water initial divided by well of our temperature final. That should be good. And so now we need to find the pressure of our water. Water pressure, it's going to be P, pressure vapor, of our temperature final, and the pressure of our air. We need to find our pressure of our air, and that's going to be the moles of our air times that R value, times that R value, times our temperature final again, and then divide by our volume of our vapor pressure. And then we're going to return the pressure of our water plus, again, pressure of our air is going to be equal to the total, minus the pressure of our final. That's going to get us our return value. A similar equation to our PEQ1, we have PEQ2 now, and we've added our total volume here as our one spot. But we still need to do a little bit of tweaking to these equations to return our moles of water vapor that we actually need, not just our desired moles. And we need to make some guesses as well. So let's switch this up, and we're going to start with our volume of vapor pressure equation, and we're going to subtract what we guessed. So our moles of water vapor desired, and we need to multiply by the molecular weight. We could multiply by the actual molecular weight, but it would help if we needed a different code to just use the stuff we already have in the toolbox. So we'll just say molecular weight, and this needs to be divided by 1,000. Okay, that should be good. So we already have our temperature final and our density here. So, and our pressure of water should be good. Our pressure of air should be good. And then we also need to look at not just our desired moles of water vapor, but what's our actual moles of water vapor. And it's going to be a pressure of water times our volume of vapor pressure divided by R times temperature final. So this is the equation we came up with on the board. And to return this, we need to have two return values. So we need to have this one that we already have, and then another one. So moles of our water vapor minus the moles of our water vapor desired. Yes, and that should be good. So now we're going to move on to the next part, which is returning our stuff. So getting our roots. We're going to use a root solver, and we're going to say root, not rod, root, of our PEQ2. And now we need to make two initial guesses. So my first initial guess is going to be my initial temperature, and my second initial guess is going to be based on a bunch of different factors, but right now we're just going to guess 0, 1 based on what we know about the moles and the size of this container. We're going to guess 0, 1. So let's make a guess. These are our guesses right now, and let's run it. Let's see if there's an error. There is an error. There's an error in here as well. Might have an extra. Maybe an extra. Oh, perfect. Found it. Let's see our roots. Okay. problem here. Everywhere else is good, but there's a problem here. So PEQ2X. There's a problem here. Volume of our vapor pressure equals volume of total minus, okay. We might need to add some parentheses or take away some parentheses in 4. Oh, it says N, the moles of water vapor are not, or desired is not defined. So let's go up here. It looks like I defined it right up here, but maybe there's some syntax errors going on. Desired is not defined. It looks like our problem. Let's see if we can put it in. Okay, there needs to be one more here. Oh wait, no, we're good. Here, and then this one. Should go with that one. That one should go with this one. Perfect. Let's try to put it this one in parentheses. Did I add one for me? Let's try that. Okay, still not defined. That one closes that one in. This one closes this one in. Which one closes this in? Yeah, that should be right. It should be right. Divided by the density. So basically all I had to do was restart and run all, and it found that this moles of water vapor was desired, came back up, went through the equation, and came back down here. It just didn't know that it was there yet. I had to restart and run all. So here we've we've gotten our root from our equations, all of our equations here, and it looks like success is false. So this is not what we want at all. This means one of our guesses might be a little bit off, and I'm gonna guess that it's gonna be our temperature rather than our volume, because I'm pretty set on our volume. So our temperature, what we got from up here, 366. This is what we got up here. So we should guess something around 366 for our temperature, because we've already gotten it. So let's try that. Let's try something 366, and let's try to run it. Okay, now we have success true, perfect, and this is more accurate to what we want. We have 0.005, that's closer, and 325, that's closer to what we would rather have than what we had before, where our code wasn't working. But that's it for me. Thank you, and thank you for watching.